Yeah, let's start reading from the sparse autoencoder section. So I don't know what.
Arshad,
Yep.
I just dropped by. I have been waiting actually for Plumber to come whole day. He didn't show up. He was supposed to show up half an hour back. So I might not join back if he showed up. If he doesn't show up, then I'll join back. Okay.
Okay, no worries. No, thank you for letting me know. And yeah, so we're going to do 3 sections: sparse autoencoders, variational autoencoders, and generating fashion MNIST images. And yeah, we'll catch up at 15 minutes past.
Okay. All right.
Okay, so yeah, speak to you later, guys.
Okay, bye.
Right, bye. Oh, hey, Otto.
Hey.
Yeah, so I'm not sure if Dinesh will join us, so we'd better get started. Wow, this section was really heavy. I must confess I don't know a lot about autoencoders. So we will do our best. We might have to listen to what the guys in America have to say tonight to understand some of it.
Yeah, I don't have any experiences after Encoders too.
Yeah, I've got a couple of questions on it, but I'm sure we won't know the answers. But yeah, so let's begin anyway. So we're going to start with these sparse autoencoders. And okay, so this is another kind of constraint that often leads to good feature extraction is sparsity. By adding an appropriate term to the cost function, the autoencoder is pushed to reduce the number of active neurons in the coding layer. Yeah, so what we're trying to do is instead of making it just copy input to output, to try and convince it to actually extract some features between the encoder and the decoder. And one way is to kind of limit how many neurons are actually active in the encoder / decoder to see if we can get some better latent representations. So it says, for example, it may be pushed to have an average of only 5% significantly active neurons in the coding layer. This forces the autoencoder to represent each input as a combination of a small number of activations. Yeah. And then they've got a little description here. So a simple approach is to use sigmoid activation functions in the coding layer to constrain the codings to values between 0 and 1, and use a large coding layer, for example, 300 units, and then add some L1 regularization to the coding layer's activations. And the decoder is just a regular decoder. So we've got here an encoder which is a sequential of a flattening of the original image, a dense layer, which is CellU, and then a dense layer, which is a sigmoid. And then we've got an activity regularization layer. And then the decoder is a standard decoder, which is kind of the opposite of what we were doing there. And so there's an explanation of what this guy is doing. So this activity regularization layer just returns its inputs, but as a side effect, it adds a training loss equal to the sum of the absolute values of its inputs. This layer only has an effect during training. Yeah, so that's interesting. So the layer just returns its inputs, but it has a side effect. It adds a training loss equal to the sum of the absolute values of its inputs. Yeah. Yeah, so that's interesting. So what's that going to do? So the loss is going to be artificially increased if the
that's like adding L1 norm on the outputs of encoder layer. And L1 norm, it usually enforces sparsity of the activations.
Right. So make the activations lower because you're adding this absolute value on top. The loss function. To decrease the loss function, the activations have to be reduced because that's how this this loss function will work. Okay, cool. So they have got like an example. So this is the sparse autoencoder. So this is without that sparsity. This is the kind of output that you get from it. And then let's have a look. So there's some functions to help plot various things. And so this is a plot of the activations before you've added in sparsity. And then let's add in the regularization. And yeah, while that's training, yeah, that's a little bit slow actually. And then the binary cross entropy and activity regularization in the encoder. Yeah, okay. They might have some pictures. Yeah, so it's interesting. So the reconstructions, are they better than the earlier ones? I can't tell. They look pretty
It's
similar.
hard to tell.
Yeah, I guess at this level, it's more the feature, the classification is what it might help with, rather than the actual generation of the output. It's always probably going to be a bit fuzzy. But yeah, might as well carry on actually.
I
We've got
wonder
quite
if he has a convolutional autoencoder example in this notebook.
I don't think in this one, because reading the chapter, they're all really to do with the sparseness with this KL divergence. He hasn't got any convolutional type stuff in the current sections that we're reading today.
I see, because he is working with images, and he mentions in the book that there exist convolutional autoencoders, but
yeah,
makes
yeah,
it very simple.
yeah. Yeah. For some reason, he hasn't actually covered those. I guess GANs are, they're the more common now, rather than the sort of sparse, or even the other autoencoder which we're going to cover. Okay, yeah.
Yeah, on the other hand, that recent, I think the paper is not yet published, but there was a post by OpenAI about that DALI. It's like combining a language model and image generation.
Oh, okay, and that's using CNN type encoder, autoencoder. Oh, okay, that's
I'm not sure,
interesting.
but it uses variational autoencoder. I think they referenced. Yeah, I haven't went into the details of it. But have you seen the results of that generation?
Yeah, cool. Yeah, this is really interesting. So yeah, the activations are very low now, but still, we're getting very interesting results. So yeah, really interesting that that this approach works. Although it depends on how much sparsity you've added, I guess. Cool. So yeah, so this is where the L1 norm is added on. Okay, so and says another approach which often yields better results is to measure the actual sparsity of the coding layer at each training iteration and penalize the model when the measured sparsity differs from a target sparsity. We do so by computing the average activation of each neuron in the coding layer over the whole training batch. The batch must not be too small, or else the mean will not be accurate. Yeah, so that's a slightly more complicated way of doing that if you were to set a target sparsity rather than just using this L1 regularization. Okay, and then we've got this thing called a KL divergence, and says one approach is by simply adding the squared error. So we're looking at the loss function that was going to be changed. But in practice, a better approach is to use the Kullback-Leibler divergence, briefly discussed chapter 4, which has much stronger gradients than the mean squared error, as you can see. So the KL divergence is this guy. Yeah, so that has got a much stronger gradient than the straight line, which and the slightly more shallower mean square error. Okay, interesting. So given two discrete probability distribution P and Q, the KL divergence between these distributions noted DKL PQ can be computed using sigma pi log of pi over qi. Okay, I mean, it's an interesting formula. I've not really come across it before. I must have, I wasn't probably paying full attention when they covered this this notion of the Kullback-Leibler earlier on in the book. And yep, so I think you probably understand this better than I do, but is there any other comments before we kind of carry on to this bit that you want to mention?
I don't think so. It's well, the formula is somewhat complicated at first glance, but I think it's what it does is pretty straightforward. It penalizes like difference in distribution. So we want our activations to be distributed with given sparsity, and if actual distribution differs, it's penalized, and that's pretty much it.
Okay. So this guy will be 0 if pi and qi are actually the same, because p over q will be 1 and log 1 is 0. Okay. Yeah, I get it. And there's a slightly different formula for it. Okay, so it says once we have computed the sparsity loss for each neuron in the coding layer, we sum up these losses and add the result to the cost function. In order to control the relative importance of the sparsity loss and the reconstruction loss, we can multiply the sparsity loss by a sparsity weight hyperparameter. If this weight is too high, the model will stick closely to the target sparsity, but it may not reconstruct the inputs properly, making the model useless. Conversely, if it is too low, the model will mostly ignore the sparsity objective and will not learn any interesting features. So yeah, there's an interesting kind of hyperparameter potentially that you can use to control how much it kind of learns. And there's some code related to the KL regularizer. Okay, so what's this comment? After training this sparse autoencoder and fashion MNIST, the activations of the neurons in the coding layer are mostly close to 0. About 70% of all activations are lower than 0.1, and all neurons have a mean activation around 0.1. About 90% of all neurons have a mean activation between 0.1 and 0.2, as shown in figure 1711. Yeah, so neuron mean activation. Yeah. So yeah, I guess it does what it says it'll do. It'll push the activations to be lower. Okay, so we move on to the variational autoencoders. So another important category of autoencoders was introduced in 2013 by Dietrich Kingma and Max Welling, and quickly became one of the most popular types of autoencoders, the variational autoencoder. So they have a quite different. They are quite different from all the encoders we've discussed so far in these particular ways. They are probabilistic autoencoders, meaning that their outputs are partly determined by chance, even after training, as opposed to denoising autoencoders, which use randomness only during training. And most importantly, they're generative autoencoders, meaning that they can generate new instances that look like they were sampled from the training set. And then both these properties make them rather similar to restricted Boltzmann machines, but they're easier to train and the sampling process is much faster. Okay. I must confess I've not studied RBMs, so I'm not quite sure how they compare to RBMs. Have you studied these restricted Boltzmann machines? Okay, and then yeah, so we carry on, and then there is a diagram of a variational autoencoder. So what we got an input, a hidden state, and a hidden layer and a hidden layer. And then the output are two sets of codings. One is a mean and the other is a standard deviation. And then from the mean and the standard deviation, we sample to get the final output of the encoder. And then we used those sampled values to then regenerate a possible output. Yeah, so then, yeah. I mean, I can understand what the diagram is saying, but I must confess I don't have like a good intuitive idea of what it's doing there.
I think it's pretty straightforward. So the encoder produces some embedding of the input or encoding, and then we perturb this encoding, and the decoder starts from this perturbed version, not from the encoding itself. And yeah, here what this picture at the right shows. I think it's that what our initial distribution we have, the encoding ends up being close to normal distribution. Mm-hmm. So, yeah, so the output of encoder is closer to be, outputs are closer to being distributed normally, and we induce some Gaussian noise. So, and that slightly shifts the encoding, but it will be like similar to the original encoding, but somewhat randomized.
Yeah, yeah, I can sort of understand that, but I mean, the confusion I have is that let's say that I mean, let's assume batch size is 1, and we've inputted an image here, and then we've gone through one dense layer, another dense layer, and we've got now some vector representation. And so the question is, how do we compute the mean and the standard deviation of that? Because it looks like they compute a mean and a standard deviation for each dimension in the output, and then when they are regenerating it, they regenerate that using this sampling, which was to take the mean and then apply this Gaussian noise to it. But unless, I guess, it's the mean across the whole batch. I mean, I'm trying to work out what exactly is this mean and what is this standard deviation of.
Yeah, it seems to make more sense if it's batch mean and deviation, but yeah, maybe we can look at the code and it will be more evident.
Yeah, it's interesting actually. Yeah, we'll have a look in the code in a moment, because that doesn't do actually any mean or any standard deviation. So I'm like, how's this working? But yeah, okay, let's carry on. So as you can see in the diagram, although the inputs may have a very convoluted distribution, so this is like this weird distribution, a variational encoder tends to produce codings that look as though they were sampled from a simple Gaussian distribution. So it's made it into a kind of like a round, and I guess the dots are dispersed in a Gaussian way. And then during training, the cost function discussed pushes the codings to gradually migrate within the coding space, also called the latent space, to end up looking like a cloud of Gaussian points. One great consequence is that after training a variational autoencoder, you can very easily generate a new instance, just sample a random coding from the Gaussian distribution and decode it, and voila. So yeah, I understand that, the decoding aspect of it. Okay. So now what we've got, there's two losses here. The first is the usual reconstruction loss. So that's comparing what the output is, and you can use cross entropy for that. And then there's a second loss, which is the latent loss, that pushes the autoencoder to have coding that look as though they were sampled from a simple Gaussian distribution. Okay. It is the KL divergence between the target distribution, i.e. the Gaussian distribution, and the actual distribution. Okay, so that's going to be pushing stuff towards the Gaussian distribution. Okay, so yeah, that makes sense. And then, yeah, so the latent loss, which was just kind of mentioned based on like the KL divergence. So the Kubli cleavage, KL divergence. Okay, so a common tweak to the variational autoencoding architecture is to make the encoder output gamma, which is log sigma squared, or because we are using that over here. And this approach is numerically more stable. Okay, it speeds up training and is numerically more stable. Okay, that makes sense. Okay, so let's have a little look at the code here. So here we've got now a sampling layer, and then that takes as the input the mean and the log variance. And then it uses a random normal of that shape, and then multiplies it by the variance, and then adds the mean. So yeah, so it's kind of sampling that in a kind of a normal distribution way, that space. Okay, so that makes sense, in that the mean and the log variance is given. Yeah, that's fine. And then let's have a look at what it's doing. So here we're saying the coding size is 10. So the input is an image, 28 by 28. We flatten it. Then we have a dense layer, cell U. Then we have another dense layer of dimension 100, which is cell U. And now we have the codings mean, which is a dense layer of the coding size, which takes as input that dense layer. And we have another layer, which is the codings log variance, which is another dense layer of coding size, which again takes as input what was the output of that. Then we sample these two layers. One is the mean layer and the other is the codings log variance. And then finally, we the encoder is the inputs are the inputs and the outputs are the three things: the codings, mean, the codings, log variance, and the coding. So this is the bit I was confused by, because these are, I mean, that's not a mean of anything, and that's not a standard deviation of anything, but somehow, I guess it must be based on the loss function that's causing these things to behave as if they were mean and standard deviation, I'm guessing, because there's no mention of mean and standard deviation anyway. So that's the bit I was confused about. I don't know. What did you think?
Yeah, that makes sense. I think that's how it works.
Yeah.
So yeah, we like force this outputs to be close to mean and standard deviation by the loss function. And here is this comments which indicate that indeed that's what's happening.
Yep. Oh, is that in the code? That yep. Oh yeah, mean and standard deviation. And so it says, note that the dense layers that output codings, mean, and codings variance have the same input side, the outputs of the second dense layer. We then pass both codings, mean, and coding variance to the sampling layer. Finally, the variational encoder model has three outputs in case you want to inspect the values of the mean and the codings log variance. The only output we will use is the last one, codings. Now let's bid the decoder. Yeah, and the decoder is relatively simple. It's just a standard decoder. For this decoder, we could have used the sequential API. Okay, I'm not quite sure what that's got to do with anything, but finally, let's build the autoencoder. So it's a variational encoder, and then we've got the reconstructions, variational decoder, and the autoencoder is the inputs and the outputs. Okay. Note that we ignore the first two outputs of the encoder. We only want to feed the codings to the decoder. Yeah. Lastly, we add the latent. We must add the latent loss and the reconstruction loss. Yeah. So it's that guy, which is the latent loss. And and then so that we're adding an additional loss to the autoencoder. K-mean, yep, and then compiling the whole thing. Yep, okay. So it says we first apply gradient 715 4 to compute the latent loss for each instance in the batch. We sum over the last X series. Then we compute the mean loss over all the instances in the batch, and then we divide the result by 784 to ensure it has the appropriate scale compared to the reconstruction loss. Indeed, the variational autoencoder's reconstruction loss is supposed to be the sum of the pixel reconstruction errors. But when Keras computes the binary cross entropy loss, it computes the mean over all 784 pixels rather than the sum, so the reconstruction loss is 784 times smaller than we need it to be. Okay, yeah, so there's some technicality to do with that, and divide the loss by 784. Yeah, let's have a look at the code. I don't know if maybe we can run it. Okay, so that's that bit. Yeah, variational autoencoder. So this is the sampling guy. And then we've got set the seed, TensorFlow seed, and the random seed. Oops, what error was that then? Codings equals. Okay, K is not defined. Okay. Did I miss that? Where is K being used?
It's probably Keras backend.
Yeah, here we go. Oh yeah, here it is up there. Oh, there's a the divergence is up there as well. And then if we go back here and then run this guy again. Oh, it's 25 epochs. Let's have a little look. So this is the dense codings, and then inputs, outputs, take the coding restrictions, latent losses. Okay. While we're waiting for that, so show reconstruction, so variational autoencoder, and then we're generating fashion images. How are we doing that? So there's a plot, and then we got a random seed. We create a random normal of shape 12, the size of the codings, and then use the variational auto decoder, pass in the codings, and generate the images. Okay, that's interesting. So yeah, While we're waiting for that, because that's going to take a little bit of time, we might as well just have a look at the final section, generating a fashion MNIST images. So now let's use this variational autoencoder to generate images that look like fashion items. All we need to do is sample random codings from a Gaussian distribution and decode them. So so we've got, so we're going to generate 12 images. So that's 12, and the coding size, which we already said was 10. So we're gonna run. Okay, so we're going to sample. Not using a normal distribution, and then we're going to pass those codings to the decoder. Okay. And then the majority of these images look fairly convincing, if a bit too fuzzy. The rest are not great, but don't be too harsh on the autoencoder. It only had a few minutes to learn. Give it a bit more fine tuning and training time, and those images should look better. Okay. Is it finished training yet? Oh, it's 17, so it should be finished in a minute. Oh, I should have chosen GPU. Sorry, I forgot to set GPU in the settings for this notebook.
So it's actually very quick, right? So if it trains in 7 seconds on CPU, it's fast.
Yeah, it's quite impressive. Because it's quite, although it's the size of the input is, I guess, not big. It's only 28 by 28, but yeah, it is quite nice that it's able to do that. Yeah, it's almost finished now.
Yeah. This latent loss part is the most interesting, I think, of this variational autoencoder.
Yeah, I mean, the fact that it pushes the representations in the way that it does. I mean, that's really clever. I hadn't thought about how you could possibly do that. Okay, so let's generate some images. Oh, that's interesting. Yeah, that's quite good. So let's have a run this guy. And then, okay. Actually, let me just print the codings, because I'm interested in what the hell the codings look like. Are they just 10 random numbers? Print codings. Ah, interesting. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 8, 10. Yeah. Yeah, just random numbers in a space, and end up producing these things. That's really quite interesting. Yeah, let's rerun it. Actually, let me get rid of the print. Okay, skip it a little bit. Oh, I'm setting the seed. I'm going to comment that out for a second. Hash, where's hash? So that I can generate something a little bit different.
Yeah.
Oh yeah, yeah, this is really cool. Yeah, really interesting. So yeah, now let me just see.
We can prime this decoder to generate something we want by entering some specific encoding.
Yeah, so one of the reasons I'm really interested in this is that a lot of times in NLP, if you're building your own data set, you just don't have the volume of data that you possibly need. So I was looking at ways of taking a limited data set and then kind of using these kind of techniques to augment that data with others that are within the kind of same sample distribution, but perturbed in some obviously slight way, so that to build a slightly more robust model. So I don't know, I haven't really looked into it, but yeah, all this stuff is like really, really cool. The fact that you can actually do this. Particularly the fact that this Gaussian model, it's each time it's doing something really quite interesting. I mean, I thought maybe sometimes it might produce something kind of like in the middle, between the two, or do something a bit strange. And but actually each time whatever you're getting is within a well-defined. I mean, you can tell whether it's a type of shoe or whether it's a type of dress. Or yeah, this is really cool. Yeah, sorry, I don't know very much about this area, but it's just looks just so great.
Yeah, it's pretty fun that you can make those things just out of thin air.
Yeah, well, we saw earlier in the chapter there was these kind of images of faces generated. I think they must be GANs, but they looked amazingly realistic. Did you see the link that they provided earlier on in the chapter to those? You probably, if you haven't.
I think I saw it some time ago. This face GAN, it's called, right?
Yeah, okay. Okay, let's have a look. It probably is using that, but it's okay. Okay, let's have a look. This person does not exist.com is, I mean, as I said, I was just amazed. The quality of this is like absolutely astounding. Obviously, these are probably hand-picked examples of what was generated, but there's such high resolution. And they're just so good. It's unbelievable. So
you can't possibly make any like.
Yeah, because yeah, I mean some of the examples I've seen, you could tell it wasn't like quite a real person. Maybe the eyes weren't quite right. There was just some artifact, of the fact that this was slightly artificial. But all of these guys are like, yeah, I mean, this is extraordinary, isn't it? It's amazing. Right. So yeah, let's have a look at the.
Totally realistic. Yeah, that's fun.
Yeah, that site is like really amazing. There's another one which does Airbnb rooms as well, which is really quite good as well. And okay, so yeah, so that's the bit where we were just looking at. Then
I wonder if really those are like picked pictures, or if it always generates such a good ones.
Yeah. Oh, okay. You can tell something really weird happened there. Yeah. That's the sort of thing I would expect it to do. But yeah, it's not doing it in real time. I mean, you can tell it's gone a little bit strange, kind of up there, but the main face area is actually pretty good. Yeah. So not all of them are like fantastic, but some of them are like really very, very good. I don't know. I can play with this for hours. Yeah, I'm sad like that. I'm amused by very simple things. Yeah, so I mean, I think I need to study some of this stuff a bit more because I guess the autoencoder paper those guys, although the generative stuff is really probably more worth studying than this paper, although the sparsity and all those kind of things. Yeah, I mean, that might be worth knowing. So I don't know if it's worth looking at any of these papers in our stuff, because I know we're NLP, but actually some of these techniques could really come in handy with augmenting data sets and yeah, particularly if you don't have a lot of data.
Yeah, the DALI model is like a good opportunity to have a look at autoencoder, like this generative autoencoders, and that is related to NLP. So they.
Yeah, cool. Yeah. Actually, I might have a look at it. I haven't chosen it. Unfortunately, I was a bit busy, so I haven't done anything for tomorrow. But maybe next week, I might want. I mean, I don't mind volunteering to have a look at that paper and try and understand it and present it.
Yeah, I'm not sure there is a paper. It's more like a blog post. I think the paper is not published yet.
All right, let's have a look. I thought I saw something on Arxiv. DALI Arxiv. Oh no, you're quite right. Oh, it's a blog post. Yeah, you're saying, yeah, DALI creating images from text.
They don't have much details on implementation, I think. but yeah, the results are really interesting, and it's still very interesting to see what this model can do.
Yeah, yeah. Yeah, I mean, or I might do this paper, you know, this, I'm hoping they will have explained it a bit more, the, or something on the, this, you know, how exactly how this works, because, I mean, okay, I think we can kind of guess what it does, but it might be worth having a look at this paper. I might have a look at it because I'm quite interested in how they did this sparsity and pushed, you know, and the loss function, and how that's causing this behavior that's actually happening, because it's not intuitively obvious that that's what it should be doing.
Yeah, they have some reference in that blog post, DALI blog post. They have some reference to some variational autoencoder paper, I guess.
Okay.
And maybe it worth looking at.
Yeah. Autoencoder. Okay, so there's an actual introduction to autoencoders. And I went, oh, okay, so this is the same guys. And I wonder how big this is. Oh wow, that's a long one. that may take a few weeks to do.
Yeah, but it might be not so intense if it's
yeah.
introductory paper.
Yeah, so it looks like it's about 50 pages. Is well, 60 pages is where it cuts to the conclusion, and then there's a whole lot of appendix. It might be still worth doing. Yeah, let me download it and potentially have a look at it, see how far I get.
Yeah, that's pretty interesting stuff anyway.
Yeah, it's worth knowing. As I said, you know, it's augmenting data is going to be next. And yeah, let me just pop it on there for a bit. Yeah, I'm really heavily interested in data augmentation, because I mean, I don't want to have to spend 6 months building up a data set. So anything that helps.
I remember something about using variational autoencoders was mentioned in that back translation paper.
Right.
So, but I think back translation worked better for NLP in most cases. But yeah, there are probably some applications of this technique as well.
Yeah. Cool. I think that's it for today. Because they're going to be, this is the section they're going to read up into, and then the generative they're going to do on Sunday, starting from this section. So yeah, unless there was anything else, I think that's about it.
Okay, then see you tomorrow.
Yeah, so unfortunately, I haven't really prepared my paper. Will you have had a chance to read that switch transformers one? Or
Yep.
I know you've been super busy.
Yeah, I've read it, and yeah, it's a pretty technical paper. So there is a lot of like nuances of implementation, but in general, it's like 30 pages long, and it's quite interesting. So
okay, yeah, great, yeah. Yeah, let's have a look at that, and I'll see if I can do this variational autoencoders by next week. Although if worst case, it might be the week after. But yeah, let's do that.
Okay, cool.
All right then. Thanks. I'll see you tomorrow.
Yeah, see you tomorrow.
Right, bye.